I think the medical school has spent some inordinate amount of money on each classroom so that that it's automatic. All right. We got money? Yeah, not really. Let's see here. I will begin with a word of prayer. So, Heavenly Father, we thank you for this day. Again, Lord, I just pray you help us to use this time wisely, just to encourage these students just do their best on the final for this class and all the other classes, that they would just finish this semester well, Lord. In your name I pray. Amen. So you guys got questions in particular? If not, I'm just going to go back to test 1 and just kind of...
It's actually in test 1, and it's problem 10, test 1. It's trigonometric substitution, right?
Right, so we got integral of x cubed dx divided by 9 minus x squared, and
X could be 3 sine x.
let's see here. Right, so let's work it out. We have the integral. So what was your question? Do you have a question in particular, or you just...
Well, I got it wrong on the test, but the logic to me is it all makes sense, so it's obviously don't fail.
Yeah, well, I can't say what you specifically got wrong in your solution there, but we can try to work out the other. Maybe it'll pop out at you when we do this here. So you said let x equal to, you tried 3 sine theta? 3 sine, sine x. We can't do that because we have to put theta. Did you put x?
I did theta, sorry.
Okay. All right. Yeah, sometimes people, when they get confused, they'll put an x there, and that just, I don't know what that means. But anyway, it means that they were taking a test and they made a silly mistake, so it means. But anyway, 9 minus x squared would be 9 minus 9 sine squared theta, which of course is, right, so the square root of 9 minus x squared then would be the square root of 9 cosine squared theta, which would be 3 cosine theta. Now, so that's my denominator, 3 cosine theta. And then my x cubed, well, that's 27 sine cubed theta, right?
Yes.
And how about my dx? Well, my dx is 3 cosine theta d theta. Missed the dx?
No, I missed x cubed.
Ah. So with that, then we've got, well, the cosines cancel, right? And we got the integral, the 3's cancel. We got integral 27 sine cubed theta d theta. So how do you do such an integral? As follows, we do that 1 minus cosine squared theta, right? Sine theta d theta. And we make a u equals to, make a u equals to what? U equals to cosine theta. Let's see here. What I should have done is asked you, what's your second guess? That's right. But it's too late. U equals cosine theta. Du is minus sine theta d theta. Right? And so what we look at, what we got here is the integral of 27 1 minus u squared times minus du. So you can integrate that. And I'm going to, one more step. Well, I'm out of board space here, so this gives me what? That gives me right, minus 27. So 27 over 3, though, right?
Oh, sorry.
And be careful with the minus. But yeah, that's minus 27 u, which was, what was u? U was cosine theta, plus 9 cosine cubed theta plus a constant, right? Now I'm told to leave my answer as an algebraic function, right? Is that, I mean, even if I put that back in terms of x directly, I mean, the sort of lazy thing to do would just be say, oh, well, theta is, inverse sine of x over 3, and just plug that in. That would be an okay answer if it wasn't for my instructions, which are to leave my answer as an algebraic function, right? So I need to figure out what are the algebraic functions that I can get from the, so we got to draw the triangle. So I'm trying to get it here. Put theta here. My substitution is that sine theta is what? Sine theta is x over 3, right? So that suggests to me that the opposite side is x, the hypotenuse is 3, and then whatever's left over is the adjacent side. So by the Pythagorean theorem, what? You say it's square root? Right. Well, 3 squared, this plus that has to give me 9, right? So it should be 9 minus x squared. Of course, that's not surprising because that's what we...
Oh, yeah. Okay.
Right. As a check, we should be able to see that the adjacent side plus the opposite side squared gives me back the hypotenuse squared, right? So from this triangle, it's apparent that cosine theta is what? Yeah, square root of 9 minus x squared divided by 3, right? So that gives me that this is minus 9 times the square root of 9 minus x squared. And then plus 9 over 27, the square root of 9 minus x squared cubed, if you like. If you want, that was a 27 over 3. I just simplified it. The 27 is there, and the 3 comes with the cosine. Of course, we can clean this up, right? My final answer, minus 9, square root of 9 minus x squared, plus 1/9? No, 1/3, yeah, I can't do math. That's here, 1/3, 9 minus x squared to the 3/2 power plus a constant. So there you go. Of course, you could factor out a square root of 9 minus x squared if you were so inclined, but I'll leave it like that. And well, I still got calculus 3. Let's see here. I got in 1. Yeah. The trash can's always full this time of day too. It doesn't help me. So if we look, here's my answer from the answer key. As you can see, I got a minus 9 square root of 9 minus x squared, 1/3 plus 9 minus x squared, 3/2. So. Oh. Yeah, okay. So there's more than one way to do it. And this is the simplification I was just blathering about. You can factor out a root 9 minus x squared there if you wanted to. But anyway, basically all 4 of the last expressions there, they're all algebraic functions, which are the answer. So I'd be a jerk if I took off points after you wrote those down. But I might give you bonus points if you simplify it nice. But on the other hand, if you simplify it and make a mistake, I'll probably take a point off. These are the things that you have to weigh, Anyway, other questions for test 1? We're talking about which problem, test 1? First one, all right. Is it integration by parts? How do we do this first problem? What manner of madness is this? Yes, I'll go over it again. I think it's helpful for us to look at this without the solution, right? That's why I post these blank tests, is so that you can check yourself. Can you actually do the problems, right? If you just study for my solution, you're tricking yourself, right? You need 2 things. You need the blank copy and you need the copy with solutions to check yourself. And then, of course, you could possibly do it a different way than I do it, like we just found out in the first round. What's that?
I didn't check, but do you have a blank copy for each test on because I thought there were
If there isn't, I meant to put it there, so let me know. Okay, so we've got what, 2 e to the x, cosh x, and we're supposed to integrate this over something, right? 0 to log 3, huh? All right, so this is the integral from 0 to the natural log of 3. And what is cosh x? What's your second answer? A second? Plus, all right. As a quick check, if you're right, cosh of 0 should be 1. Cosh of 0 is 1, just like cosine of 0 is 1. Sinh of 0 is 0, just like sine of 0 is 0. So cosh and sinh and sine and cosine, they're counterparts. They all agree on what 0 is, should be. If you put a plus here, then you get 1/2 of 1 plus 1, which is 2 over 2, which is 1, so it works. That makes sense, right? So, and then the 2's cancel. When we multiply this 2 times that half, I'm just left with e to the x times e to the x plus e to the minus x dx. And yeah, I suppose you could use any number of integration techniques here, but you'd be wasting your time, right? Because the first thing you got to do is just algebra. So this is the integral from 0 to log 3 of e to the 2x plus 1 dx, right? And then we just integrate, right? I mean, use substitution if you like. So we got 1/2 e to the 2x plus x. Evaluate that from 0 to log 3. What do you get? Can we simplify that? I think we can. Yeah, that's 9/2 plus the natural log of 3 minus 1/2. In other words, it's 4 plus the natural log of 3. Well, so e to the 2 natural log of 3 is e to the natural log of 3 squared, which is 3 squared, which is 9. And then the half just wrote along. Other questions about test 1? Let me just take a look at the solution for a second here. Let me just kind of give you a lightning tour through it. So problem number 1 is really just about, have you appreciated what cosh is? Have you internalized what is the hyperbolic cosine? And do you know basic facts about it? Right? Because if you do, this integral is not hard. If you don't, if you're kind of half understanding cosh, this integral becomes very difficult. Problem 2 is really a calculus 1 question. I'm not likely to ask that on the final. All right. The reason it was in this course is because, unfortunately, not all of you have had a proper calculus 1, right? And of those of you who have, you've probably forgotten a lot of it, right? Now, this second one is pretty obviously an integration by parts, right? X times sine, integration by parts. The next one, you got partial fractions, right? You set up the partial fractions. Got to be aware of the different cases to think about there, right? Like if we have a linear factor repeated versus if we have an irreducible quadratic, they behave differently. The setup for the decomposition. Hey, let's just make up one and see if we can do it, huh? I'm not going to actually do the algebra, but like at least set it up, you know? How about this? Suppose you have f of x equals to x cubed plus 7x squared plus 42 divided by x, let's see here, x to the 4th minus 64 times x squared plus 1. So what would be the partial fractions decomposition for this function? So before you can do that, you first need to do what? You need to factor the denominator completely over the reals. So x to the fourth minus 64 is really what? I'm going to work on that over here. Yeah, that's x squared squared minus 8 squared. So it's the difference of perfect squares. So that's x squared minus 8 times x squared plus 8, right? But this is actually x minus root 8 times x plus root 8 times x squared plus 8. If you don't mind, I'm going to change that x squared plus 1 to an x squared plus 4x plus 5, just for the sake of making sure we know what we're doing. Okay, so this is, we just figured out, is x plus root 8 times x minus root 8 times x squared plus 8. So that's, again, that's just the x squared minus 60, x to the fourth minus 64 factor. That's as far as I can go, right? I cannot factor further over the reals because x squared plus 8 is irreducible, right? It has no real 0. And how about the other term? Yeah, complete the square on that. That will reveal its true nature. In particular, that is x plus 2 squared plus 1. And so if you complete the square and you get a sum of squares, that goes to show that this is irreducible over the reals. It cannot be further factored. It's a irreducible quadratic. So we actually have two irreducible quadratics here and two linear terms. And so now with that, I can write the partial fractions. The partial fractions will look like a over x plus root 8 plus b over x minus root 8 plus cx plus d over x squared plus 8 plus ex plus f over x plus 2 quantity squared plus 1. Right. As a check, you should have as many undetermined coefficients in the partial fractions as is the power of the denominator. What's the power of the denominator here? 4 times, the leading term would be x to the 6th, right, if you multiplied it out. This is a 6th order polynomial in the denominator. And I got 1, 2, 3, 4, 5, 6. Okay, that's at least a partial check. Yeah.
The rightmost term, we need to write the times x plus 2 plus
Oh, wait, yeah, or, right, or you could do that. That'd be fine. I would count either as right, but I prefer this answer, actually. Thank you. This is better. If we actually were going to integrate it, that would be much better. We should do another one of these, right? I think, yeah? How about this? What if I had, I'll make the factoring a little bit easier this time. What if I had g of x equals to x to the fourth minus 17 divided by, I don't know, x minus 1 cubed times x squared minus 1. So one of the things you have to watch for with partial fractions is you got to make sure that you've actually collected together all the similar terms. That's not an issue in the first example that we looked at here. But in the second one, these have overlapping factors, right? One more step. There is some factoring to do here, isn't there? See, this is really x minus 1 to the fourth times x plus 1. Because this x squared minus 1 is x minus 1 times x plus 1, right? So one of those combines, it gets lumped into the x minus 1 cubed to bring it up to x minus 1 to the fourth. And the other one's on its lonesome. And so once you have that, once you're, okay, so the denominator is completely factored, we can't do more, that's it. Now we can write down the partial fractions. The partial fractions in this case is a over x minus 1 plus b over x minus 1 squared plus c over x minus 1 cubed plus d over x minus 1 to the fourth plus e over x plus 1. That would be the partial fractions decomposition here. Again, the bottom is a fifth order polynomial. If you multiply it out, it's quintic. And as you can see, we have a, b, c, d, e, 5 variables. That shows me that at least I possibly am right. But in fact, that's right. I mean, that's what it looks like. Yep.
Okay, so like the first problem, and it was like e times the x plus 2 plus f over the x plus 2 squared.
Right.
Why do, like, so it's x minus 1 squared, why isn't it like multiplied by the...
So what's the difference between the green term and like the red terms down there?
Building up.
The difference is that this is an irreducible quadratic, whereas this is just a linear factor four-peated. So this is the partial fractions decomposition for that. I mean, I think it's, if you wanted to, this would not be the partial fractions decomposition, all right? But it is true that there exists some, I think you could write a cubic polynomial of the form, something like a naught plus a1x plus a2x squared, plus a3x cubed divided by x minus 1 to the fourth. I mean, that would cover everything that these four terms cover. I mean, that would be interchangeable with this. It's just we don't write that because it's not, well, first of all, it's not the partial fractions decomposition. Second of all, if I wrote that down, I wouldn't know what to do with it. I mean, that's true. And maybe that's more analogous to, I mean, do you see the analogy straight between this and that and this term? Right? It's like the quadratic, and then there's like a linear. Here, this is even better to look at. This one's quadratic, and then an arbitrary linear thing up front. So if I have 1 over x minus 1 to the fourth, I can rewrite that as x minus 1 to the fourth downstairs and an arbitrary cubic upstairs. But the thing is, you can take this and you can basically just Taylor expand the numerator around 1. And then when you do that, you'll get like a 1 over x minus 1 to the fourth. This one, when you expand it around 1, that will cancel to give you a 1 over x minus 1 cubed and an x minus 1 squared and just an x minus 1. It generates these 4 kinds of terms. And those 4 kinds of terms are important because these we can actually integrate. Every one of these is a basic rational function which allows integration. Getting back to your basic question, though, the difference is that one is an irreducible quadratic and the other one is a linear factor to a power. That's the difference. Let me erase this before some of you take this. This is what you're supposed to do. I do not want to see that. That's something else entirely. All right, let's move along. We have other things to cover. So problem 5 here, you know, do not fall prey to the everything is a log. Like some of you get in this habit, anytime you're faced with like, if I give you integral of dx over cosine x, some of you will just without thinking instinctually write, oh, it's the log of the absolute value of cosine x plus a constant, and then you go on, and you'd be wrong, because that's not true, right? When can we just put log? I mean, it's dx over x, most basically, that's natural log absolute value of x plus a constant, right? And if there happens to be, sometimes we can get away with like simple u substitutions like this problem, right? U equals x minus 1. But don't get carried away. You got to actually think through the u substitution. If the u I mean, if I let u equals cosine x, I mean du is minus sine x dx. Do I have a minus sine x dx here? I do not, so I cannot do that, right? In fact, this is secant, which is considerably different than that, right? Any questions on this one? The 2 options. The one is to, you could trade that x for x minus 1 plus 2, which would give you a 5 there, and an x minus 1 times 2 divided by x minus 1, which just gives you that 2. That's long division. So that long division supports the algebra there. Yeah. But if you don't see the long division, this one is kind of forgiving. I think if you let u equal to x minus 1, you can still work through it, even if you don't know the algebra. But you should know that algebra. This one was, I mean, log, if you see log of stuff, that's probably integration by parts, right? Yeah, here's one of those ones that loops. This is a very popular test question. Wouldn't be that surprising to see something like this on the final. You hate that question? Yes. That's why we like it. No, sorry, what?
So, like, I know, like, when integration by parts and loops, what do you do when you find that loops of the same term? That's where I get stuck.
Oh, if it loops back to exactly what you started with, that means that you have found an identity, which is true but useless. Like, in principle, you could do an integral, integrate by parts twice, get back to the integral that you started with, and then what you'd be left with is something like, maybe it works out to like sine squared plus cosine squared plus a constant equals 0. Well, that's true. That constant's minus 1, right? So that can happen. You, in principle, can do a loop which goes back to the integral again. What that means is you got to try something different. And yet it's something that happens, and it's an important calculational technique, so I suggest studying it. I mean, this one, after we integrate by parts 2 times, you know, we end up with n squared over a squared times I with a minus. So if you put everything with I on one side, you've got I plus n squared over a squared times I equals stuff. So factoring out 1 over n squared over a squared gives us that I is equal to that times the stuff, which gives us the answer. Yeah.
That part right there,
Where's my laser?
I think I had the same answer, but I got marked off.
You can show me afterwards. But let's see here. Next we had the. I mean, I can't look at specific tests during the file. This improper integral, right? Indefinite integral. I said make a hyperbolic substitution, so I wanted you to make a hyperbolic substitution, and that's a friendly request, because if you made a trig substitution in this problem, you'd end up with a secant cubed. Secant cubed is something you can do, but you don't want to do. Anyway, so on the other hand, with a hyperbolic substitution, we get cosh squared, which is actually not that bad. Find the volume of this thing of rotations. This goes back to how do you find a volume? We broke it up into, in this case, washers. Each volume of washer is pi r squared dx because it's got no inside. So there's no, like, it's pi r, you know, generally speaking, it's pi r out squared minus r in squared, but here r in squared is 0. So we just get pi r squared. And here, the radius was tangent, so I end up needing to integrate that, which is not that bad. Now, this was like a homework problem, was it not? So we talked about this already. Now, here's something we probably haven't thought about in a while. How would you integrate cosine 3x times cosine 5x? Well, pretty much the only way you can do that is if you know this trig identity, right? Now, you do not have to derive this trig identity by this algebra up here. That's just the way I like to do it. But one way or another, you need to know that if we have a product of cosines, we get a sum of cosines, where the angles are either the sum or the difference of the respective angles, right? So if you didn't know this, you probably should learn it, right?
Is 1/2 always there?
Yeah. Yeah. Now, I will say this. If you know this identity, you could differentiate it to get other identities. So, I don't know. So I could write this down like more generically. What is this? I think I'm getting too far into the weeds here, but I'll allow myself just this one small comment. If we have cosine of, well, basically the cosine of x times the cosine of, let's say, y, or let's say a, right? Well, that works out to 1/2 the cosine of a plus x plus the cosine of, I think, x minus a. We could look at it that way anyway. So here I'm thinking of replacing 3x with x. I'm thinking of replacing 5x with a. But the same, you can go through the same calculation there and you'll get this identity, right? So if you know this, and maybe it's even better not to do x. Maybe we should just do a and b. How about that? Let's try that again. A, b, a plus b, a minus b. How about that? What's that? Well, cosine's even, so we can't get into trouble. That if I put cosine a minus b, or if I put cosine b minus a, I get same animal. Now here's the neat thing, guys. Suppose you memorize this, right? I don't think that's too much of an imposition to memorize this, right? If you do memorize this, you can derive everything else from it. Like, for example, if I differentiate this with respect to a, what do I get? Oh, I'm sorry, there's a minus here. Right, because derivative of cosine is... And so getting rid of the minus, we've got that the sine of a cosine of b is equal to 1/2 sine of a plus b plus the sine of a minus b. And what if you wanted the sine-sine identity? Why don't you just take this and differentiate with respect to b, right? And I differentiate with respect to b here, I get a minus from the chain rule. And so there you go, sine a, sine b is 1/2. Well, we could remember this way, cosine of a minus b minus the cosine of a plus b. So anyway, there are your 3 product identities. If you remember one of them, differentiation will get you the other 2. Or you could do my imaginary exponential thing if you like it. Yeah.
Differentiating cosine A, cosine B, wouldn't that be product rule?
I'm holding b fixed. B is a constant for this differentiation.
Okay. So that's not a function. That's more of a real.
Yeah, I'm not supposing that b is a function of a here.
So, okay, that makes sense because you just took the derivative.
Thinking of b as thinking of b as a constant, and then later here thinking of a as a constant. If I vary b. But anyway, so choose one of the following problems. Ooh. So these ones are actually tough. Choose your poison, yeah.
Can we work through A again, the one on the left?
What's that?
Can we work through A, the one on the left?
You want to talk about the one on the left? I can talk about it. All right, so first of all, I suggest, man, I give you guys a substitution. That's too nice. Come on. Oh, I give you substitution over here too? Aw. I'm becoming too nice. All right, x equals to u to the 6th, then that means that dx is 6u to the 5th du, right? Now the square root of x would be u cubed. The cube root of x would be u squared. So when you put all that in there, you got this. Now that's all hunky-dory, but the thing is, this is a 5th order over a 3rd order, which means their first order of business is to what's that? What did I say?
First order of business.
Ah. First order? Oh. Oh. That was an unintentional pun, but I'll accept it. Is this it's not some kind of Star Wars humor or something? No, it's more basic punnery. Okay, so this is going to be a, let's see, you got 5 over 3. That's going to be like a quadratic plus a proper rational function looking ahead. And here's the math that does it. The quadratic is actually 6u squared. And so long division peels off the piece of it which is quadratic and leaves the other piece which is a proper rational function, which of course partial fractions will do its thing too. But this one is super nice. Like in general, when I see u cubed over u cubed minus u squared like that, what I thought was going to happen to us, this one is really quite forgiving, because generally speaking, if you got something like 1 over u cubed minus u squared, well, that's 1 over u squared times u minus 1, right? So that suggests partial fractions a over u plus b over u squared plus c over u minus 1, right? Like that all could have happened here, except something really fortunate happens in the sense that we've got u squared here, we've got u squared here, and we're just left with du over u minus 1, which makes this problem nicer than it might otherwise have been. And then you unsubstitute. Here's the wrong way to do problem 1. Yes. So this is exactly, you're asking me about, what if when it loops and you don't get this exactly. If you do integration by parts on the first one, this is actually an example where you end up with this identity. You get back to where you started, and you've got this thing is equal to a constant, which is kind of like weird because it looks like it's not constant, right? But when you actually work it out, it's minus 2 is a constant, which is, yeah. It's not like there's this dangerous set of problems where using integration by parts leads you to mathematical heresy. It's just it may or may not be useful, right? I mean, it's like it's still producing true results. It's just, you know. Here's the wrong way to do problem 11, integration by parts. It actually, you can look at it as a loopy problem. So if you don't want to remember all the trigonometry I just wrote down for you, feel free. You can integrate by parts 2 times and solve this problem still. You know, you can do integral of cosine squared with integration by parts 2 times too, but it's sure a lot smarter to know that cosine squared of theta is 1/2 1 minus cosine, good grief, plus cosine of 2 theta, right? Like, I think that beats the pants off doing integration by parts 2 times on this thing. But it's true, if you do integration by parts 2 times, it loops back, and you can derive the integral without trigonometry, without this trig. I shouldn't tell you that. Test 2? Test 2. Is it important that you know the definition of a series? Yes, it's still important. Should you know how to use L'Hopital's rule? I think I'd have a hard time getting you guys to use anything except for L'Hopital's rule now that you know it. Don't forget about, you know, L'Hopital's for powers. What was our trick? We insert an exponential of the natural log. We use continuity of the log to pull out the continuity of the exponential to pull in the limit, and then work on the limit thing. I call it star. Do your L'Hopital's on that. You get the thing, plug it back in. Whatever happens, happens. In the book, he doesn't do this. He takes the log of the limit. He works out the limit of the log, and then he puts it back in. He extrapolates from that what it is. My way of presenting work is different than the textbook here. What's the deal with this one? And it's improper, right? It's a hidden improper because the thing is log of 0 is infinity, right? Minus infinity. It's not defined really. So this has to be understood in terms of a limiting process. In particular, it should be understood as limit as a goes to 0 from the right of a to 1 of that, right? Now, I chose to find the antiderivative of this by integration by parts up here and then use that. I think that was just a, you know, trying not to bite off more than I can chew at once. So it's nice to, if an integration technique is required, it's probably smart to do that on the side as an indefinite thing and then put that together with the fundamental theorem of calculus to handle. What's a probability distribution? All that means is the integral from minus infinity to infinity of your function is 1. And also, if I give you a probability distribution which has negative values in certain places, you should probably question my question writing skills, right? Because probability should be positive, right? And it should be less than 1. I mean, you can listen to these sports people talk about giving 110%, but you should keep in mind that they're idiots. Anyway, sorry. Obligatory. Hey, people talk bad about math all the time. That makes it right, right? Do unto others before they do unto you. Isn't that the thing we're told? Okay, so limit of sequences. I hope you can do these kinds of things. I don't really have much to say about that. Approximating series. What is the one most important theorem about approximating series that you need to know? If I want to, the alternating series estimation theorem, right? That if the series is alternating, the error in what you've already summed is at most the next thing that you haven't yet added. So if you really understand that, you probably can answer my question if I ask one about this. So here, this is the alternating harmonic series, and I said to within 0.2. So the terms in this are like 1 over n, right? So I want 1 over n equal to 0.2. That's 5. So if I use the fourth partial, you know, up to 4, that should do it, because the next one, which is 5, is 0.2, right? And so that's 1 minus a half plus a third plus a fourth, which is 7/12, which is 0.583. By the way, this thing actually works out to log 2. We proved that at one point. And log 2 is 0.69 or something. So as you can see, it's actually better than 0.2. It's about 0.11 away from the real answer. So the alternating series estimation theorem tells you the biggest the error can be. It doesn't say the error actually is that big. Of course, it would be good to know the relation between rational numbers and the geometric series, right? Any rational number, any repeating decimal, rather, can be written as a rational number by using the geometric series. But you got to be aware that sometimes you have to, like, peel off something. Like here, I have to pick off the 0.3 because it's the 2 that's repeating, you know? So 0.3 is not actually part of the geometric series here. It's just sitting out. And it's this part that's the geometric series. And there it is, 5/18. We had a bunch of convergence theory, right? So chief among those is the nth term test, right? It can be that easy. If the nth term goes to something non-zero, the series diverges, right? But you should remember, when the nth term goes to 0, that does not mean convergence, right? That means it might converge, it might not. We don't know. So what's next on the list? We have the alternating series estimation. We had the alternating series test, right? We had integral test. We had the p-series. We had direct comparison. We had limit comparison. And then we had bigger guns, right? Like ratio test and root test. Sometimes absolute convergence is useful, right? Any questions about any of that? It's a relatively small part of the final. I mean, it's probably going to be there, but integration's a much, much bigger deal to me, I'll be honest. Calculation of Taylor series is a bigger deal to me than this. So if you can't find a Taylor series, if you don't know how to work with geometric series, like in the next test here, to me that's kind of a larger issue. I can live with passing somebody in Calculus 2 who, you know, has decided to use direct comparison rather than limit comparison foolishly or something like that. You know, that to me is not a deal breaker. If you don't know integration by parts, or you don't know how to find the, you know, Taylor series for sine, this to me is far more troubling. Anyway, let me shut up about that. Let's see here, what was this one? Oh, this is a geometric series, right? So how can you test whether or not a series is geometric? You just take the nth term, divide by the n plus 1th term. If when you do that, you get a constant independent of n, it's geometric. So just take the ratio of successive terms if it works. And then I almost forgot about this one, the dreaded telescoping series. There are 3 kinds of series we can actually calculate the sum of, right? That I know of anyway, that are reasonable for this course. First and foremost, geometric series, we can actually calculate the sum, and it works out pretty nice, right? It's a over 1 minus r. Geometric series are awesome. The other thing that we can actually calculate the sum of is telescoping series, like this one. You notice that I can work out, actually find a stone cold formula for the nth partial sum. In this case, 1/2 minus 1/2 plus 1 over n plus 1. Take the limit as n goes to infinity, we get a half. So there you go, we calculated the sum of the series explicitly from the definition. This is rare and precious that we can actually make this go. What's the third and weirder way of calculating the sum of a series? I don't know. Well, all right. Let's go on. Let's see here. There's sometimes we define sequences recursively, you know. I think your main weapon to remember that we can use in those kinds of problems is the monotonic, what is it, the theorem, monotonic sequences, a bounded monotonic sequence is convergent, right? Bounded monotonic sequences are convergent. Monotonic means it's what? It's either
Non-increasing or non-decreasing.
right, so I would say strictly increasing or strictly decreasing, I think. Or is that right? Or is it just, I think it may just be increasing or decreasing. But yes, anyway, bounded monotonic sequence here. This is a ratio test problem. All right, this will go on here. I want to get to the next test. We're running short on time here. Any questions yet about this before I do that, though? No? All right. Test 3. You know, so again, the heavy lifting for the approximation here is what? I mean, we use a power series approximation for the integrand, right? And once you do that, you get, you know, fundamental theorem of calculus provides us with, at the end of the day, an alternating series, right? So we can use the alternating series estimation theorem to say what the error is if I just keep the first 2 terms, you know? Now, I think here it was supposed to be within 0.001, so you might wonder how I knew that keeping the, you know, the first 2 terms would suffice. I guess I didn't. I just started calculating and I got lucky. In principle, you could work this out and find out that you needed 1 more term that you hadn't kept already, right? So, you know, that can happen to you. So to be smarter, you would actually calculate what that is when you plug in 0.2 before you get too far into the, I don't know. I just usually keep the first 3 terms and try to hope for the best. And then if worse comes to worse, I'll write down more. But there is a smarter way of doing it, but that's, you know, testing them a lot of time, so do something. All right, but there's a larger issue here, which is that how did I know that this was equal to that? What's this? Binomial series, which is one of the things you should know, right? Binomial series, exponential, sine, cosine, cosh, sinh, geometric. These are the things we should know instinctually at this point.
Sorry.
Yeah, go for it.
When you integrate 1/2 x squared, doesn't it go to 1/6 x cubed?
Uh-oh, you're right. Oh, no. Yeah, you can show me afterwards. I'd be happy to give you points back if I took points off for that. Yeah, you're right. Of course, that is the case. Yeah, that should be 1. But yeah, that is obviously a mistake. Thank you. Now the next problem, you know, how do we find interval of convergence and radius of convergence? Ratio test, right? Ratio test is the weapon of choice here. And so applying the ratio test will tell us that, you know, for x subject to some condition, we'll get convergence. And then the endpoints we have to check explicitly. So here I'm able to figure out radius of convergence is 9. That will tell me the open interval of convergence, and then I have to check endpoints. In this case, the left endpoint ends up being harmonic, and the right endpoint ends up being the alternating harmonic, which converges, the other one diverges. So there you go. This is a question which is very conceptual, doesn't really require a lot of calculation. It's a pretty good question. There's a lot of different ways to ask it, but you should try to understand this. Any questions about problem 3? The main point here is that if you have the center of the power series, if you know where that is, if you have a point of convergence that's a distance whatever away from the center, then everything up to that distance must converge. All right? On the other hand, if you have a point of divergence, then everything that's everything that's farther than that distance must diverge. All right? You can't have diverges 5 away on the left and it converges 5 away on the right. 4 away on the right. What happens at 5 is up for grabs, because you can have converge at 5 on one side and diverge at 5 away on the other side. So endpoints are a little bit tricky, but this one here, I forget what the story is here. This one's actually a little bit subtle. The ratio test actually ends up popping out a 1 plus 1 over n to the n power. That actually limits to e. And so we get ex, which means that we need the absolute value of x less than 1 over e. So my open interval of convergence is minus 1 over e to e, 1 over e. And I think I said find the open EOC for this problem. Yes?
Back to 3, how do you know if it's a bracket or a...
It depends on the data. So here I'm supposed to find the largest interval of convergence, which is possible. So I'm given that it diverges at 10, right? Excluded. Yeah, parentheses. Converging is bracket, because the bracket means that it's included in the interval. And we're always giving, we write the interval of convergence. Now, if I wanted to really confuse the students, I would sometimes ask for the interval of divergence. And then we would all be properly confused. But no, I shouldn't do that. Ooh, I should write a paper on evil ideas for confusing calculus students and make a compendium of these ideas to encourage similar like-minded professors on ways to persecute their students.
The interval of divergence would be a disjunction, right? So it wouldn't be a true interval?
Yeah, it would not be an interval. That's also true. So interval would be an abusive language. Yeah, that's true. It would be discontent. Students fight back. Yeah, that's right. Go Nathaniel. All right. Yes. Oh, okay. So find a power series centered at -2. So I have to make an x plus 2 appear somehow. To do that, I subtract 2 and add 2, which gets me this. Now that's not geometric yet. I need a 1 minus stuff to use the geometric series result. I create the 1 by factoring out an 8, and then geometric series gets me here, and there you go. The work here for interval of convergence all comes from the radius being x plus 2 over 8 here. We need the absolute value of the radius to be less than 1, which pretty much tells me the open IOC for that without no ratio test in sight here, right? Just from the geometric series theorem, I know what the interval of convergence is. So problem 5 is important that problem 5 is very, very likely something like this to be on the final. I would be shocked if I didn't put something like this on the final. This, to me, is very important. It might not be exactly this problem, but things like this, okay? Right. Now this one, you can already see that on my test, right? I didn't have one question about that. I had 2, right? So this one here is actually a little bit nicer, centered at 0. So all I got to do is create the 1 by factoring out the 7. When I do that, the 7's be canceling. And so I get radius minus x squared over 7. And so there it is. Yeah. Let's see here, geometric series techniques. This one, the 3, well, 3 is what it is. Inverse tangent, though, that does not, I mean, I guess you could remember the power series for inverse tangent, but I don't think you will. Certainly, if we differentiate inverse tangent, we get 1 over something plus 1 over 1 plus the thing squared inside the inverse tangent, right? Times the derivative of the thing inside the inverse tangent by the chain rule. So a chain rule of differentiation and the known derivative of inverse tangent gets me that. But this is resembling the a over 1 plus r formula, a over 1 minus r formula, right? So I can look at this with a equals to 12x and r equals to minus 36x to the 4th. The geometric series converts that to that. Now you got to clean it up before you integrate, though, so be careful. So 12 times minus 36 to the n, and hey. Oh man, that's supposed to be 4n plus 4. 4n plus 1. 4n plus 1 here. Yeah. Whoa. And so that should be a 4n plus 2, right? I'm going to have to take points off my test. Let's see here. It's okay. I think I curved your test already, so I made up for it there. But anyway, so that should have been, of course, 4n plus 1. That should be 4n plus 2. That should be division by 4n plus 2. Anyway, when you plug in 0, this is all 0, but we left over the c. That must match the 3. Apparently, c is equal to 3, and there you go. But the more important idea here is that we differentiate something. It gets us to something geometric. Apply the geometric series, and then integrate to get back, right? If we differentiate and then do series, we integrate to get back. There are other problems where we integrate, find the series, and then differentiate to get back. There's other problems where you could differentiate 2 times, do geometric series, and integrate 2 times to get back, but I don't typically ask you those. These are also important to me, and I don't think you guys did that well on them, if I remember right. Maybe I hope I'm wrong. It's been a long semester. I forget what happened. So make me forget properly by showing me you can do it on the final. Let's see here. And so cosine of 2x plus 1 is this, right? So you got to know your trigonometry. And once you have that, then we can Maclaurin, we know the known Maclaurin series for cosine, the known Maclaurin series for sine, we just do substitution of 2x into those, right? So you need to know. It's kind of smart to remember them in terms of theta or something, because then, you know, if you remember it in terms of theta, you know, and it's also good to remember the first 3 terms. So if you know that, right, and you know this, which is, by the way, first 3 terms, theta minus 1/6 theta cubed plus 1 over 120. I guess I could put a 24 here, whatever. Theta to the 5th. Then you can, you know, it's easy enough to make a substitution, right? So like here, what have I done? I've put theta equals to 2x, right? And over there I put theta equal to 2x also. So, you know, and for a problem like this, I say find the first 3 non-trivial terms. That means non-zero. You know, do you want to use the big clunky full power series for this? You know, no. You want to use this, right? You want to use what the first 3 terms are. So, you know, what's the right weapon of choice? This one here